Well, thanks everyone. Thanks for the introduction and thanks for having me. Special thanks to Claire. Claire and I work together. She's one of the organizers here, so that's how we made the little connection. Few sentences about myself. Before I joined Elastic, I did everything from pen testing, vulnerability research. I even worked in law enforcement for a couple of years. And at Elastic, I focus on malware research, malware reverse engineering, and I have a slight preference for looking at a Linux malware. Adjusting the mic. Yep. So yeah, as I said, I have a slight preference for looking at Linux environments, Linux malware. That's where most of my research is done. Another fun fact about me, I have about 55, 56 slides with me today. That is a lot. My strategy to get through that is not to take my ADHD medication and speak really fast. I'm here for the rest of the day, so if I went through it too fast, just come up to me. I'm happy to do it once or twice or 5 times again. We can make that happen. So, a quick disclaimer in the on the title, you could see the word Vectorsearch. People associate that with AI. This talk is not about AI, Gen AI, any hype, buzzword, whatever you like. It's not about that. If anyone is disappointed about that, no? No? Awesome. It is about, still Vectorsearch, it is about technologies like TLSH. It is about disassemblers. It's going to be about malware, code, assembly code. But it's mostly a story. It's story time. It's fun time. It's things that I've discovered that I had no knowledge of. I have no business talking about. Still, I'm on stage. So, but it's going to be fun. And after that broad statement of not being a person to talk about AI, let's start off with an AI-generated image. Also, fun thing. No, what you see in the image, it's a little bit of a symbol, a kid trying to get a ball off a roof using tools that were not made for doing that. I would not suggest getting on a chair using a rake to get that ball. Just call your dad. That's easier. But let's start with the chair. Let's start with Vectorsearch. By the show of hands, and just be honest here, who knows what Vectorsearch actually is? Okay, I see 2 hands. Out of those 2, I'm going to take you as voluntary victims now. Do you actually know how Vectorsearch works? I'm going to explain it, but meh. Okay, then the whole audience is at the same level as I was last year, so that's good. I'll take you through the entire journey. What is Vectorsearch? Now, these days we have all these machine learning models. Take ChatGPT, for example. They need to store their data in a format somewhere, but you can't just store machine learning data in a normal SQL database. You can't ask a machine learning model to say, give me the next word in the sentence by doing select star from blah, blah, blah. You need something more specific to that use case. So someone invented Vectorsearch, and Vectorsearch is a database, let's call it a database type, where you can find data types that are close to each other. Now, what do I mean by that? At the basic, how Vectorsearch works is you've got stuff. You give that stuff to something magic. We call that a machine learning model. And at the end comes out numbers, also magic. Again, this is where I was at my knowledge level about a year ago before I started this research. Now, that stuff, let's make it really practical. Let's make a machine learning model that is gonna tell you if an image is either realistic or it's a cartoon. And it's going to give you a number between 0 and 1, and that number is, if it's 0, it's going to be really realistic. If it's 1, it's going to be really cartoonish, and anything in between there is a number. Now, let's make that machine learning model even smarter and teach it the difference between mammals and birds. So if an image looks a lot like a mammal, it's going to be outputting a 1 and a 0 for a bird. Now, we've got 2 numbers. And 2 numbers on a graph make coordinates. And that's exactly how you should imagine working with Vectorsearch. something has a coordinate, and that coordinate can be close to other things. So if for example, you want to ask, hey, I've got this image on the left side of the screen. You want to ask that machine learning model, how similar is this image to other images that you know? Well, it'll analyze that image, give you the coordinates of that image, and then you can do a lookup and see, hey, I've got this image placed at a certain location in my vector search database, and everything around it is similar. So that is how models like ChatGPT find out that if I'm speaking a sentence and it wants to figure out what word is associated to cat, it'll search the vector space for location or stuff that is in the same location near the word cat. Now, let's make it really technical. And the next slide, I hardly understand, so don't beat yourself up. But what is actually close to each other? You have several methods of finding out what in a vector search database is close to each other. If you take the three big dots on the, let's say, left, that they're connected by a triangle, A, B, and C, those are close to each other. Why? The Euclidean distance, as they call it, is 8. They're equally far apart. So in that method of determining what is close to each other, those three dots are exactly the same. You can also do cosine analysis of the data, and then you have that line all the way at the bottom where you can see A, B, and C following the same line. That follows the same angle from the starting point, and that's cosine similarity, meaning that A, B, and C on that line are similar. Completely forget about everything I just said. It's just background noise, but that's the way of thinking about similarities. Also, this is two-dimensional. People can imagine this in 3 dimensions, but most machine learning models work on 300 to 7,000 dimensions. These calculations become very complex very fast. So let's stick with this, two-dimensional. That's all you need to know for now. Now, I've done a couple of presentations internally at our company, and I've heard people saying, hey, the learning curve of using vector search and other technologies, it's very difficult. It's you need to teach people how to use it. It's hard to imagine. You need certain skills to use it. It's not that hard. It's really, really not that difficult. And that's my personal opinion. I've got people that will beat me for this, but I'll give you a few examples. Starting with our own example, if you do a vector search query, this is the entire request that you would send to a server. You tell it, hey, this is the vector that I'm searching for. These are the numbers that I'm searching for. Give me the top 5 most similar ones. Of course, we're not the only ones to do something with vector search. You can use Postgres, for example, to do the same thing. This is a very simple looking query for the SQL gurus under us. In a few lines of code, you can do a similarity search. And recently, even SQLite got a update, or a plugin, I should say, a VSS that supports exactly the same thing. So even in SQLite, you can do vector search in just a simple query. It does take, let's say, an hour or two to figure out the documentation, know what you're doing, but it's as simple as this. This is all it takes. Now, the second technology that I want to talk to, and we'll bind everything together. This is just me rambling a little bit, but is TLSH. Again, by the show of hands. Anyone know what TLSH is? No? Oh wow, this is amazing. I love this. TLSH is the Trend Micro Local Sensitivity Hash. Now, normal hashes, I'm guessing SHA-1 hashes, MD5 hashes, stuff like that. Everyone probably knows what that is, right? I see people nodding. That's good. That's good. Local sensitivity hashes are a little bit different. If you input some data into an hashing algorithm, normally you would expect if you change a single bit, then the output is completely different. That's with the randomization and how those crypto algorithms work. In local sensitivity hashes, that's not the case. If you change a little bit in the input, the output will change a little bit. And if you get the output of two calculations, you can calculate how much the difference was between the two inputs. This is great for finding, what's the English word for this? Yep, not getting it. If someone steals your text and so uses it as their own, I'm not finding the word, but you can use that to find similarities in the text. Trend Micro, of course, an AV company, published this algorithm, and they use it to find similar malware samples. So let's say you have a malware family, there's a new version of it, a slight modification. You can use this algorithm to calculate how much difference is there between the two pieces of data. Now, these hashes look like just random numbers, but in fact, they have a format. You have the version, you have a checksum, and then you have the actual hash bytes. Now, remember when we were talking about vector search, these hexadecimal bytes, you can actually translate them into what I would call today a vector, a list of numbers. Also good to remember, a vector, if a machine learning expert is talking about that, vectors are a list of numbers. Let's keep it simple. Now, those TLSH hashes look really similar to vectors that we use in vector search. And someone mentioned like, hey, we have vector search now these days. Can't we use that to find similar malware samples? Spoiler alert, yes, we can. But one of the more important things is you have two TLSH hashes. I can calculate the difference between the two. I can't predict how the output is going to look based on the input. That means that I can't have a sorted list of TLSH hashes, which will tell me, hey, these files are all similar. The only way to find the similarity is to calculate the difference between two hashes. That's important to remember. Now, I've got a few Python examples. In this example, I generate two sets of data. I calculate two TLSH hashes. I calculate two SHA hashes. And of course, the output, as you would expect, is exactly the same for data 1, data 2, because the input is exactly the same. And all the hashes are the same. In example 2, I changed the first byte of data 2. And the output of the SHA hash actually completely changes. And you can see in practice, if you look really to the far right, there's a 0. And in the second hash, that turned into a 1. Now, last tool. Does anyone recognize this tool? No one? BinaryNinja? Never heard of it? One person. Amazing tool. I love it. I work with this every day. What this is a disassembler. Imagine you get malware, binary samples, you get them at your desk. Your manager asks you, analyze it, give me some information about the files. Now, one of the first things that I do is put it into a disassembler. The disassembler will take apart all the functions and give me nice graphs and assembly instructions. This is what I look like, what my work looks like on a daily basis. Now, while I was working with this assembler, I realized that the whole file that I'm working with is a collection of bytes, nothing special. And a collection of bytes is exactly what you give to a hashing algorithm, like SHA or TLSH. But these functions, these instructions, machine instructions that I'm analyzing on a daily basis are also just a collection of bytes. And what you see in red are the bytes representing the machine instructions. I thought, could I just not give these to a hashing algorithm? Turns out I can. And that actually started the research that I did during one of we have own weeks. That means that we have a week where we do absolutely nothing productive. We can do just research whatever we want. And this was the research that I did during one of our own weeks. I realized, hey, if I put this function data through a TLSH hashing, put it into a vector search database, I can then find functions that are similar to each other. So I spent some time coding that up, and a few hours later, this was my output. What you see on screen is a function offset in a binary, that's the second column, which is exactly the same as a function offset in another binary. And what you see all the way on the right are the labels. And what I noticed here is that I have some functions that I find in Black Matter ransomware that I can also find in Logbit ransomware. I was pretty impressed until I found out that 2 months before that, the researchers at Sophos found exactly the same thing. Now, I'm a positive guy. You could say, hey, your research has been scooped. You did everything for nothing. No, I figured out that my research actually worked. My method worked. And what I wanted to do is automatically disassemble every malware sample that I have, put everything into a Vectorsearch database, and just hit a button, do my work. Now, I went on, I found even more overlap. Klopp ransomware had functions that are the same in Ryuk ransomware. Phobos and Logbit had overlapping code sequences. So, awesome. It's really going somewhere. Now, there are some constraints, but I'm going to talk about that later. Back to the disassembler. I mentioned one of my specialties within Elastic is looking at Linux malware. Now, Linux has one thing, and that is it runs on a lot of architectures. You will see a lot of malware that's running on MIPS, ARM, ARM32, all kinds of different things that you normally don't see on a desktop PC. Now, take for example, I have this little C code, does absolutely nothing special. But if I compile this, put it into a disassembler, then I get this as my output. On the left, you will see the output if I compile it for a Raspberry Pi, which runs on an ARM v6 processor. And on the right is the output for an x86 system. Now, in the middle, you see the byte sequences. And if you look at them really carefully, you see that they're absolutely not the same anymore. Meaning that my complete idea of taking these bytes, vectorizing them, putting them into a Vectorsearch database, and finding similarities goes down the drain instantly. Well, luckily, disassemblers nowadays are way smarter than me, which is not that difficult, I admit. But disassemblers can translate assembly instructions into intermediate language, and then eventually into pseudo C code, but making the work of the life of the analyst a little bit easier. What you see here is the same two functions, but then processed by the disassembler, and you will see that even though a lot of stuff is different, the structure of the function is the same. It's basically recovered. Which means if I do a TLSH calculation and compare the two functions after that, I get a difference value of 60. Now, that doesn't mean that there's 60% variance. 60 is an arbitrary number, and it changes by how big the input function is. A normal threshold is 80. Anything below 80 is considered roughly the same. Now, that means that that I now have a second option. I can do the same calculations, but just use the intermediate language processed or given to me by the disassemblers. And that makes me happy, because now I can use plugins like this. I can open up my disassembler. My disassembler will automatically do a request to a Vectorsearch database, find all the functions that it already knows about, and it'll give me some information. Makes my life as an analyst way easier. Oh. Now, of course, that's not the only use case, and this whole talk isn't specifically about just this use case. It's about using techniques in a way that it's not supposed to, not built for it. I know a lot of hackers try to use the same mindset, but Vectorsearch was developed to support machine learning models. It wasn't made for this. We do have some multiple use cases that we now use it internally, but just keep in mind that this mindset. Now let's talk a little bit about constraints. Vectorsearch is a new technology, and a lot of development is going on. Slides. First, one of the constraints, code quality. TLSH was a interesting project. It was released a couple of years ago by Trend Micro, and after that it was abandoned. And we can see that it is really abandoned. We have issues there. For example, a memory leak that makes it basically unusable, and Trend Micro isn't addressing it. Probably internally it is, but the external algorithm isn't maintained. Luckily, one of my coworkers took it upon himself to make a C++ version of the library. If you want to use it, this is the link. However, I'm obligated to mention this. He said I can mention the fork, but I'm not supposed to say that it is any good, so I've done my due diligence. Claire, make a note of that, please. But no, Chris did rewrite the entire algorithm. This is the fork that I use internally now, but yeah, there's a lot of still issues with it. Another thing is, we analyze roughly 1 million files per week. And by we, I don't mean manually. We have very smart people like Claire that make pipelines to make sure that we analyze all these files automatically. But out of every file, I can extract over 200 functions. Do a few calculations, and that means that I would need to store 10.4 billion vectors per year in a database. Now, you would say, okay, 10.4 billion, it's a big number. Databases are meant to support big numbers. Yes, indeed. But for vector search, the entire data set needs to be in RAM, in memory. So if you do a quick calculation about how much RAM that I need to have a single copy of 1 year's worth of functions, I would need roughly 0.5 terabyte of RAM. Now, I don't know about you, but when I went to our director and said, I need a database cluster with about 1 terabyte worth of RAM because I need some duplication, he laughed me in the face and said, try again. That's not happening. That's expensive, especially for a research project. Now, I mentioned that this space is moving very fast. There's a lot of interest in AI, in machine learning, in LLMs, and also in vector search. That means that you talk to a lot of people that are developing these solutions, as did I. And while I was talking to Benjamin Trent, that's one of the core vector search developers at Elastic, but also an open source Lucene developer, very smart guy. He was looking at my use case, and he said, Remco, those hashes, those are bit vectors. And I looked at him and I said, yeah, probably. I don't know. You would know better than me. You're the expert. And a month later, I was talking to him again, and I said, Remco, I have something for you. You should use a hammering distance. And I looked at him in the same way and said, yep, you're probably right. I have no clue what you're talking about, but if you say so, then. Turns out that calculating a hammering distance is something very easy, and vector search developers are now implementing that into their products. What is it? Take the two... Oh, I made a typo. Take two hexadecimal values, convert those into ones and zeros in binary code. The second one should have said 1B at the end, so excuse me for the mess up there. But if you convert a hash into a binary value, then do an XOR between the two, and you then count the number of ones that are in the result, then you can use that to find the distance between values. Now, I don't know if I'm making any sense, but this is really fast and really efficient, and it's, again, a new algorithm that's being implemented. Also, the good thing about this is, if you know something about CPU architectures, doing an XOR takes exactly 1 CPU cycle. So this calculation on a modern CPU can be done 3-4 billion times a second. Going back to my 10.5 billion vectors that I need to analyze, I no longer need to store those in memory. I can do a lot of calculations on a modern system, and I can use this this new technique. Now, this technique is completely unimportant. Just forget about it. The reason why I'm only mentioning it is if you have an idea and you talk to the correct people in the community about it, they will start thinking about it. They will start developing it. And especially in a world where we live in today, where a lot of new code is written, a lot of investments are made, as in AI, you can use those techniques for other purposes as where they were for initially developed. And that is also my closing remark. Is this the best solution for the use case? Probably not. Probably there are better algorithms that are easier or even more efficient hashing algorithms that I could see. But this was a easy to implement, readily available solution for a problem that I was facing. The whole concept of disassembling these functions, doing hashing, storing them into a vector database, and finding similarities took me maybe 20 hours of work. And I knew nothing about machine learning, nothing about vector search. Like I was you. Like half a year ago, I just had to open the documentation and find out how does this work, for God's sake. And it's readily available. So think about the techniques that you work with on a daily basis. Think about new developments that are taking place in the world, and maybe you can combine the two, figure out a new solution. And that's it. If you want to reach me, these are a few contact details. I will be here for the rest of the day, including the after party. If I need to repeat anything, if you have any questions, then I think I have 15 minutes left. Thank you. Any questions? Awesome. There you go. Yeah, there is an algorithm that's widely used, if I'm pronouncing it right, SSDeep. That's one commonly used. You will see that in VirusTotal. There are other algorithms, but I don't know them by name. And actually, TLSH uses another algorithm in the back end and does something smart with that. Yeah, there are other LSH algorithms, definitely. Yeah. I saw another question. Well, I think, let me just, this one, between, I think, Phobos and Logbit. I didn't expect that one. Sorry, too many slides. Yeah, Phobos and Logbit, that was somewhat surprising because we just thought Black Matter and Logbit were working together. Phobos apparently had a similar overlap. Yeah, Clop, that's an interesting one. While I was working at law enforcement, I used to deal with two major attacks where Clop was deployed. So I really didn't expect to see that in my results. That was definitely a surprising one. Anyone else? Gentlemen. 8 gigabytes. Yeah, that's way better. Yeah. Anyone else? I guess not.